call a viscous suspension will be a collection of a large number that will be called capital N of small rigid particles. Okay, and you put these particles inside some viscous fluid. And for simplicity, for the talk, I will stick to spherical particles, B1, Bn, with centers x1, xn, and a radius r, which, as I said, will be small compared to the typical length scale of the flow. So this typical length scale will be introduced typically through the forcing in the fluid equation. And then once you have put everything in dimensionless form, this typical length scale is 1. And okay, so what is the model what is a possible model to describe this? Regarding the fluid part, we will make an assumption which is very common in this kind of context. We neglect the inertia. Okay, so we are left with the Stokes equation outside the complement of the balls here. Okay, this omega n. And there is a forcing term as promised, F. And of course, accordingly, I impose a no-slip condition at the boundary of the particles, which means that the velocity field of the fluid, U, at the boundary should be the velocity field of the particle. And as the particle is rigid, you can describe this velocity field by some linear velocity VI and some angular velocity omega I. Okay, so there are n particles. And so now I have to describe the evolution for these VI, omega I, and xi's. And naturally, you will describe this evolution through Newton's dynamics, where you can see here these last two relations that correspond to conservation of or to evolution of linear momentum and evolution of angular momentum. Okay, so this m here is the mass. This matrix J here would be the moment of inertia of the particle. And this sigma of UP, as usual, is the Newtonian stress tensor. Okay, so just to fix notations, this d of u is the symmetry part of the gradient. But as you will see a little bit later, we will simplify a little things, and we will neglect inertia as well in the particle dynamics. Okay, so I will put these acceleration terms here to 0, and this will give rise. I want to point here on the board, but I should do it on my screen. So this will give rise to okay, this set of reduced equations n prime, where I have a balance of forces and a balance of torques. Last remark. So now I have the full model, right? And the last remark is that I will consider situations where there is no contact between the particles. And as you will see, this makes sense. So I mean that when you take two different centers, that should be distant at least from 2r. So now it is very easy to see that if you are in this setting, if your particles are far away, I mean, are not touching, then given a reasonable source term f and given my positions, velocities, you can solve the Stokes equation. Okay, and you get a solution U, say in H1 or homogeneous H1, which will be a functional, of course, of this capital X, which is the set of xi's, this capital V and this omega. And moreover, if you remember the no-slip condition that was there, it's linear in V omega. I mean, in an abstract form, you can then plug this U inside the Newton's relations, and you are left with an ODE. Okay, so what we are considering here is an ODE on the XV omega, but of course, you don't really want to look at it as an ODE system. And okay, if you are in the inertialess regime, capital N prime, then you can decompose a bit, meaning that you can have a look at the balance of forces and torques, and this will give you a linear system on the velocities, Vi omega I, and it's easy to see that this linear system is invertible. Okay, so then, okay, these VI's, omega I's at the end of the day will depend only on X, and then you will put that in the relation X dot I equal VI, and this means that once again that you will get an ODE, but which is this time only on the positions. So what we want to know is how this system of ODEs behaves. And of course, the first question is, do we have solutions? Okay. So what is pretty easy to show is that you will have solutions as long as there is no contact between the particles. And it turned out that this is always the case, meaning that there is this recent result by Aléa and Sabag, very recent, where they show that if you start initially from balls that do not touch, then they will never touch. Okay, so in particular, the solution of the ODE system is defined globally in time. And I will explain a little bit, but later, why there is no contact occurring in this kind of models. Okay, but this is, of course, a very nice property. And this allows me to be on a safe ground and to go to the main topic, which will be an asymptotic behavior when n goes to infinity. So we will be interested in the behavior of the fluid velocity un and positions and velocities of the particles when n goes to infinity. And as many times in this conference, we would like to see a reduced PDE model appearing somewhere. Okay. And for the talk, not only for the talk, actually, we will restrict to the inertialess setting. Okay, we will restrict to the inertialess setting where we are able to say a bit more things. So if you are in this setting, you can think of this whole model as the coupling of two blocks. So you have the PDE block, okay, made of the Stokes equation, the no-slip condition, and the balance of forces and torques. Okay, and then you have the ODE x prime equal v. Okay, so of course they are coupled. Okay, it's a dynamical problem because the particles move, but sometimes, okay, you want to relax a little, and you will, you may want to have a look. I mean, you may want to say, okay, I freeze the time, okay, and I will look only at the PDE block, given the positions of the particles. Okay. And then, okay, you say that at this given time, these particles satisfy some good properties. They can be well, geometrical, they can be statistical. I will give you a few examples. So typically, what you can assume is that, well, at least what is assumed in math papers is that the empirical measure converges, okay, to some limit density rho, which will be nice enough, let's say bounded, and which will okay, be supported in some bounded domain that I call capital O, just for notational to fix notation. And of course, a special interesting case is the homogeneous case where this limit density will be a characteristic function. Okay. So that's one kind of assumption that you can see in the papers around these suspension problems. There is another one, which is an assumption on the minimal distance between the particles. So this is obviously the kind of assumptions that probabilists hate, but okay, you will see you will see it appearing in this talk. Another kind of assumption that can be made is stationarity. In the following sense, you can imagine that okay, you give yourself a small parameter epsilon, you give yourself a bounded domain, okay, and you give yourself a stationary point process on R3 of intensity 1. And then you rescale it by epsilon, and you say, okay, my x1, xn are those particles that fall into my domain O. Okay, so typical homogenization point of view, I would say. You can even push further the assumptions, add some mixing and so on. Okay, but of course, you are taking a risk when you make such assumptions that they will not even be satisfied locally in time. Okay, but okay, sometimes it works. Okay, so okay, now I go back to this. I mean, to the full model. Okay, to the full model evolving in time, and I'm interested in this asymptotics as n goes to infinity. And a good place to start is dilute suspensions. Okay, so I will first consider the case where the solid volume fraction is small. So the solid volume fraction, this is this phi here. So you have the ratio between the volume of the n spherical particles, the ratio of this to, let's say, the volume of a domain containing this particle. But of course, there are many ways to build some dilute suspension, and there are two opposite kind of ways. You can play on the interparticle distance. Okay, so typically with this kind of assumption on the distance between the centers, or you can also get a dilute solution by removing balls. Okay, so through more like scening. Okay, so I will try to evoke these two kinds of, and I will mostly focus on the first one. Okay, so when you assume, then you can try to relax the assumptions. Okay, but let's start from an assumption on the minimal distance like this one. If you start from this, then you can make progress on the understanding of these asymptotics through what is known as the method of reflections. So what is this method? It's just an iterative method that allows you to solve this n balls problem with a sequence of single balls problems. Okay, so you can do that. You can in this way build some approximation of the fluid velocity, and you can do the same for the particle velocities. Okay, and okay, and you do it in the following way. I'm interested in the fluid velocity, for instance. Of course, as a start, I will take the solution where there is no ball. Okay, so this is my U naught here. But doing so, of course, I cheated because there are balls. Okay, so there is a mistake that is made on the balls BI, the particles BIs. Okay, so I have to add some corrector, and I will add for each ball BI a corrector UI1, which corrects the error from the previous step, but which will neglect all the balls around. Okay, so this will be a solution of a Stokes equation outside ball BI only. And then, of course, so yeah, that's written down here. So you have this Stokes equation, as I said, outside the BI. Okay, here you have this no slip condition, which is modified by the error term due to the previous step. And okay, through Taylor expansion, actually, as the ball is small, you can approximate this error by some linear or some affine vector field. Okay, so there is a constant contribution, there is this contribution of the curl, and there is also a contribution of the symmetry part, which is very important when you look at the effective viscosity of these suspensions. Okay, but of course you can iterate the process, because now the correctors that you have added, this UI1, well, the UJ1, they all create an error on ball BI, and so you can correct this error on ball BI by a one ball corrector and so on. Okay, no problem with this iteration. And so, of course, the advantage is that you have explicit solutions at each step of the iteration, because you are solving the Stokes equation outside one ball, so you have an explicit solution for that. Okay, so everything is very nice, and so typically, then you are allowed to replace your full velocity field by an approximation like that, which is explicit. You will have some approximation for the particle velocity, so you can put it in your ODE system and compute with explicit formulas the evolution in time, right? And this is I mean, I find it surprising how well it works, because you see, for instance, on this picture, on the left, you have the result of a numerical calculation on this reduced ODE model with 3,000 beads following their centers. And on the right, you have a real experiment where they put some beads of glass in some silicone oil, and they look at the sedimentation. And so, as you see, it's really striking how. Okay, but I'm not interested in the finite n behavior, which, by the way, can be very complicated. So I'm trying to look at the limit n goes to infinity. And for that, I have to say a few more things about these one ball solutions. Okay, so first there is a general comment where you can already understand what will be the type of limit model that you can get. This is a comment which is valid for any Stokes solution outside any obstacle. No need for a ball here. You just write down the Green's formula, and you can express in this way the Stokes solution in terms of its stress tensor at the surface of the particle. And the expression involves this capital J, which is the Ozin tensor. So it's a Green function of the Stokes operator. Okay, so it's a matrix valued function, and this is explicit, well known, and this is homogeneous of order -1. Okay. And so you see from this expression that if you look at the behavior at large x, or I mean when x is away from the ball, which will be less and less constrained as n goes to infinity, because as I said, phi is small, so r is small compared to n minus 1/3. So when I will send n to infinity, r will go to 0. Okay, and of course, if x is far away from the ball, you can do some kind of asymptotic expansion in negative powers of x minus xi, and so you have something which is very analog to what is called multiple expansion in electrostatics. So you see, you have the first term which is homogeneous of order -1. And if you see it as a function in R3, it satisfies the Stokes equation, and with the source term, you will have a Dirac mass. Then you have a term which is, so this is an equivalent of a monopole in electrostatics. Then you have the equivalent of a dipole, which is homogeneous of order -2, and solves the Stokes equation with a source involving derivatives of Dirac masses and so on. So you may already see that this approximation through the method of reflections will lead to Stokes equations with Dirac masses or derivatives of Dirac masses on the right-hand side. And then depending on the setting you consider, there will be one kind of term and not the other. And asymptotically in n, the systems will be a bit different. So here I talk about suspension, but for instance, you can do that for the famous Suranescu-Murat problem, you know, of the strange term coming from nowhere, but actually it comes from there. So if you look at sedimentation, for instance, that means you look at the case where you have no forcing in your fluid, but you consider the effect of gravity on each particle. Okay, the right scaling here is 1/n. Okay, no torque as well. And then you can do the computation, and you find a solution that is called a Stokeslet. So this is the first part here, the Stokeslet. You have a complementary part, but which will vanish when n goes to infinity. And this is the expression outside the ball. Okay, so yeah, you have this guy outside the ball, and inside actually you have a constant. Okay, because I'm not dealing with points here so far. I'm still with balls. Okay, and but of course, okay, so this is continuous across the ball, but the derivative will not be continuous. Okay, so when you apply the Stokes operator to this guy, but seen as a vector field on R3, where you have the constant inside the ball and this expression outside, what you find is a combination. So it's almost like the empirical measure of the exercise, but of course you cut at the surface of the ball, so you replace the Dirac masses by the Dirac at the surface of the sphere. Okay, but it's the same. It's the same, meaning that now if I take the limit n goes to infinity, I have this formula. I mean, I see that the Stokes equation the effective model should be something like that, involving the density rho at the right-hand side. Okay, so that's what will appear in an effective model for sedimentation. Okay, the second example is effective viscosity. So effective viscosity. Okay, you have no gravity typically, and you have a forcing in your fluid. Okay. And then you look for some effective model. So again, you can compute a solution explicitly. I won't enter the detail, The leading term of this solution is homogeneous of order. Okay, there is a typo here. It should be homogeneous of order -2. So I forgot an x to the 5 at the denominator here. And also it involves, you see, the stress matrix of this U naught, so the symmetric part of the gradient evaluated at xi. When you put that in your approximation, okay, and you look at the Stokes equation that it satisfies on R3 again, the main change is that you don't have an empirical measure at the right-hand side, but you have the divergence of a term with the empirical measure. And then you can send n to infinity. So you get this effective term that appears at the right-hand side, but this is not very convenient because it involves the unperturbed solution. Okay, it involves the unperturbed solution. But of course, you see from this equation that the effective velocity field and the unperturbed velocity field will differ by phi. So you can actually replace this U naught by the effective U without, I mean, and it will be consistent at order phi squared. So at the end of the day, actually, you can rewrite the whole equation like this, where you see that the original viscosity coefficient, which was 1, is replaced by some variable coefficient, which involves the limit density of the empirical measure.
Sorry. What is phi again?
Phi is the volume fraction. It's a solid volume fraction.
That makes sense.
Okay. And okay, so you see that the effective model is a Stokes equation with a modified viscosity coefficient. And in the homogeneous case, when rho is constant over the domain where the particles stand, you find that in this domain, the effective viscosity is obtained from the original one by adding 5/2 of phi. Okay, and this is a very, very popular formula in this business, which is due to Einstein. Okay, so this is formula. This is Einstein's effective viscosity formula. And so everything I said here about the Stokes equation, because I focused on the Stokes equation, you can do some formal derivation at the level of the particles as well, and translate this when n goes to infinity into some transport equation on rho. Okay, so there will be a coupling in the effective model. I will show you the final model just in a few minutes. Okay, so that's really this idea of the method of reflections that gives you the effective limit, the effective model, and you can go further. But of course, now comes the question of its justification from a mathematical point of view. Okay, can we justify this approach? The answer is yes, partially. But there are difficulties, and those difficulties are related to the fact that the vector fields that enter this approximate scheme are quite singular. Okay, you have term homogeneous of order -1, homogeneous of order -2, typically. Okay, and so this creates two kinds of difficulties. First, there is a bad thing that they don't have a so good decay; they are not so much localized, and also they have a singularity at the origin. Okay, and so this will create difficulties. So, for instance, due to slow decay, it can be hard to show when you sum these one ball solutions. So you sum them from 1 to n. Okay, and when you send n to infinity, if they do not have good decay, you don't have integrability. It can be hard to show convergence. Okay. So that's one obstacle due to this slow decay. And then when you have this, because of this singularity at the origin, when you look at the ODE part of the model, you will face the classical difficulties related to mean field limits with singular kernels. Okay. So these are the two main sources of difficulties. But things can be done. So for instance, in the context of sedimentation, the first example that I gave, you can really derive an effective model within, I mean, under two different sets of assumptions. Either you say that the radius is of order 1/n, And then you are allowed minimal distance between the particles that are of order n minus 1/2, and you can show that it will be preserved through time. Okay. Or you allow for larger volume fractions, but still vanishing when n goes to infinity. And then, well, you have to restrict even more your assumption on the distance, on the initial distance between the particles. Okay, you will assume that they are distant n minus 1/3 from one another. So, okay, in this kind of context, for instance, you can use some mean field methods and derive this coupled system. Okay. Which is a coupling between the Stokes solution U and the density rho. And then you can study this system on its own. I won't discuss that. Okay, and regarding the effective viscosity problem.
Just a question for notation.
Yeah.
So what is the meaning of one CP gamma? I don't understand how we.
Oh yeah, sorry, I forgot. Sorry, yeah, that's a typo. I forgot the gravity here. Yeah, there is the J, the G. Sorry, the gravity. Okay, the gravity. We are in the sedimentation problem, and that's the contribution of gravity. Sorry. Okay. And okay, regarding the effective viscosity problem, you can again derive a coupled system under this set of assumptions on phi and on the minimal distance. So I really think that would be interesting to investigate more these kind of problems, because we know from the lectures of Pierre-Emmanuel that mean field limits, these problems around mean field limits have known that there have been breakthrough results. Okay, and it would be really nice to implement, to see if it's at least usable in this context. Okay. But of course, there is one main difficulty, which is that the kernels that appear or that are hidden behind are not so repulsive. It's not so clear. Okay, but the main obstacle to more general results is really at the level of the mean field. Because if you look at the sub-problem, as I was mentioning about Stokes, looking at Stokes, then you can have quite general results. For instance, okay, so here I have to make assumptions on the positions of my particles, but I can have very mild assumptions in the sense, for instance, that we are able to prove that Einstein's formula is true if you assume for the particles that, okay, you need a little bit than no touching. Okay, you need an epsilon room, and then you express the fact that this is dilute, saying typically that the number of particles that are so this would be the number of I such that there exists some j xi minus xj is less than eta n minus 1/3. This cardinal should be less than eta to some positive alpha times n. And so this is really the kind of assumptions that is satisfied for many point processes and all. So this is not a very demanding assumption. So at the Stokes level, we can do better, but this is the mean field part that is still to be understood better. And still, if I stick to this Stokes problem, actually you can go further, because what I described here through this Einstein's effective viscosity formula is really the first order correction in the solid volume fraction file. Okay, and so what we did a couple of years ago with Mathieu Hilleret was looking at the quadratic term, which forces you to see pairwise interactions. And when you do the calculations, so typically through this method of reflections, you see that the second order correction to the effective viscosity should be given by, I have a limit which is missing here. You should have a limit of this kind of guys where this big M here is a singular operator of degree -3. So it's a Calderon-Zygmunt kernel. Okay, and actually this is not just a remark. I mean, we really use the fact that it is Calderon-Zygmunt to be able to derive this phi square term. And okay, this is just, I mean, a little comment, but okay, the first remark is that the limit is not expected to be 0. So which would not be the case if M was smooth. So everything comes from the singularity. And okay, what we found nice here is that this problem of finding the limit of this kind of mean field terms connects very much to works of Silvia Serfati and co-authors in the analysis of Coulomb gases. Okay, there are ideas from this field that you can really import here. And then, but of course, in the analysis, in the works of Silvia Serfati, the xi's are given as a minimizer, I mean, as a minimizer. But while here you sort of make some stationarity assumption. So at some point, of course, the two analyses differ and you use homogenization arguments to conclude. Okay. How much time do I have left? 10 minutes, maybe. So, okay, I will not go too far here. So I mentioned the case of dilute suspensions where when the particles are far away from one another. You can also have a dilution obtained through thinning. So then the method of reflections does not work so much. But you have formally a kind of substitute which is called the cluster expansion. So, okay, when you try to use this kind of cluster expansion, you realize that you need to put a lot of assumptions to sort of adapt the reasoning, and you need to really be in a random stationary setting. Okay, so maybe I should skip this. I should rather consider another point of view, which is a more a homogenization point of view. So far I thought as I mean, it was maybe closer to the analysis of the particle system, but here I would like to emphasize that at least if you look at the Stokes subproblem, there are interesting homogenization questions that arise. Because, okay, if you look at our system, so here I took 0 force, 0 torque. Okay, I'm in a bounded domain now, but it's no big deal, right? With a Dirichlet condition at the exterior boundary. So then when you look at this system, you are outside the dilute regime. So phi is away, I mean, phi is closer to 1, phi is not small anymore. Then, of course, you cannot hope for a perturbative approach. Okay, but what will save you is that we are then in the framework of homogenization. It's a degenerate problem of homogenization in the sense that you can show that this problem, this model, is obtained as a limit of a Stokes problem where you have two viscosities, one in the outside the particles and a viscosity mu that will tend to infinity inside the particles. Okay, so this problem is really a degenerate problem of homogenization with infinite viscosity in the inclusions. So you can try to analyze this degenerate problem of homogenization to have an effective model. And luckily, the analog problem for the Laplacian was studied in depth by Zhikov. In the book by Zhikov, Kozlov, and Oleinik, there is a whole chapter and actually a couple of chapters on this. And so there are, of course, many things that transfer to the Stokes case. And typically, this is a result of Durance and Gloria. If the balls are separated, I mean, okay, you need maybe an epsilon room like here. But if the balls are separated, then you can derive, as n goes to infinity, some effective model, which is again a Stokes equation with a modified viscosity matrix. And this viscosity matrix, as usual, is the solution of a correct, I mean, is associated to the energy of a corrector problem and so on. Okay. But the interesting thing is that one can go much further this separation assumption. You can prove that you still obtain this kind of limit problem as long as the clusters formed by close particles are not too big, in the sense that you need a moment bound on the diameter of the clusters of particles. Okay. In the few minutes that I have left, I will explain to you why, what is the reason behind the fact that we can go much further. This has to do with what is called network approximation, which was introduced by Borsea, Papanicolaou. There are a lot of works of Berliand around it. There is a whole monograph about it. And this is a nice tool to treat dense suspensions. But I think there are things that still need to be done, because so far the results really concern finite n systems. Okay, and here I think this technology or these ideas could be used investigating the n goes to infinity limit. Okay, so what is the idea behind the network approximation that can help to gain understanding in the behavior of the understanding of the behavior of the suspension? Well, the starting observation is that if you have two balls, Bi and Bj, which are very close, so the distance between them is delta Ij, very small, and you look at a Stokes solution outside these two close balls, then you can prove that the energy behaves at leading order like the square of the difference of the velocities on the two balls, okay, divided by the distance. This is the contribution of the drag force, physically speaking. Okay, so the drag force scales like the inverse of the distance between the two particles, and that's the reason, that's the main reason why the particles cannot collide. So that explains the global well-posedness result I was stating at the beginning. Okay, but the nice thing is that when things get close to one another, when particles get close to one another, you can sort of reduce the complexity of the model, replacing the continuous geometry by some graph where you just keep track of particles that are close from one another. And to each edge of this graph, you will associate a weight, which is the distance between the two corresponding particles. Okay, so you have this kind of discrete skeleton. Okay, what I think remains to be done is really understanding how this skeleton can tell you things about the full continuous model. What we know typically is that when you try to, I mean, the finiteness of the energy of the corrector in homogenization will correspond to the boundedness of a sequence of discrete energies on this graph, on these graphs. Okay. Okay, once you understand this, you understand that if you control the size of the clusters, it will be okay, because you see, you have to find a choice of values VIs for which this energy will be bounded uniformly in n. And so for each cluster, you will take, for each cluster, you can take, sorry, this is not UI, this is VI, this is a typo. So for each cluster, you can take VI to be this matrix S here, Xi minus S, and you take the center of mass on the cluster. Okay, and then you see immediately that this guy will be bound. Okay, and okay, as open problems, it would be really nice to understand better the connection between these discrete energies and the continuous model. For instance, when the suspension gets denser and denser, then this approximation by discrete energies on graphs should be better and better. And to see how the energy may diverge, it would be, of course, important to understand what is the asymptotics of this kind of discrete energies. But when it diverges, it means that you cannot really construct the corrector, while the solution of UN of my system is bounded in H1. Okay, so of course there is a big open problem still, which is understanding this limit of UN where you cannot rely on the corrector. Okay, and of course on top of that, you would have to add the coupling with the particles. Okay, so I think there are really open questions around this this kind of network approximation. And I will stop here. Thank you for your attention.
Thank you very much for this talk. Are there questions or comments?
Yeah, it's a really cool direction. So so have people successfully derived some of these fully nonlinear kind of active scalar equations from the particle limits, or is it still not really understood how to do that? I couldn't quite.
In the dilute case?
Yeah. Even
yes. So
case.
you have full results.
Okay.
You have full results with the mean field limit included. But okay, you have to be in the, so typically, for example, this result of Mesherbe that I'm mentioning here, when the radius is of size 1/n, so the volume fraction is very small.
Mm-hmm.
It involves results, well-known results of Maxime-Auré on the mean field limit.
Mm-hmm.
Here, the kernel is essentially of degree -1, which enters this framework. Okay. In this latter case, it's a bit, well, it's a bit different, but still you rely on this Auré method. But if you, for instance, one open question is if you push to phi small but independent of n, what can you say?
Mm-hmm.
And then you really see in your mean field limit a singular kernel, which is homogeneous of degree -2, which escapes the standard things. Okay, I mean the robust methods so far, they work for 1/x d -1, less than 1/x d -1 in dimension d. So we are in the limit case where it does not work exactly.
I see. Okay. So even when phi is very small, quite small, we still don't have a derivation.
No complete proof.
Okay.
Cool. This might be just like trying to cause trouble, but is there any hope in doing like first order inertial corrections? Like if we start to slightly leave the Stokes regime and get a little bit of inertia back into our problems, is there any hope that these mean field limits will still work?
Okay, so there is, I think, a formal paper of Papanicolaou on this in the framework of sedimentation when he tries to do some formal expansion in the inertia, and he sees some correction.
Okay.
I think the picture may change totally because you know, for nonlinear, I mean, when you look at Navier-Stokes. When you look, you have this kissing and tumbling effect, which means that there are some attractive features, attractive repulsive things. And so, I mean, regarding the mean field limit, it should be a mess. So,
have you thought about putting angular momentum in?
Yeah, so I've not talked too much about this, but it can be handled. It can be handled. Thinking about angular momentum and its effect on the suspension, it's even, I mean, there are interesting questions, but when you don't have spherical particles.
Right.
So typically when you have ellipsoidal particles, then you have additional effect due to the torque. Angular momentum is really something that plays a deep role. While as long as you stick with spheres, well, it can be handled.
Has yet attempted to derive any like viscoelastic models from polymer chains?
No, so that's really yeah. So for instance, if you take the system that was mentioned by Dallas in his talk yesterday, so that's not really viscoelastic, but that's a kind of coupling, and still. Again, I mean, it's derived by some kind of method of reflections, or at least through an approximation, through one-ball approximations. But the very bad feature is that you have when the gradient of u involved, when you do the calculation, there is again a very singular kernel, 1 over x cubed this time. So actually, I'm not really even expecting that, well, no, that this limit model could be derived. And maybe there could be issues.
Other questions or comments? If not, then let's thank David again for a great talk.